Okay, let's take a look at some sample exam questions on ordinary differential equations. I'm going to start off looking at first order ordinary differential equations in question 1. So we're looking for the general solution to a first order differential equation. dy dx is equal to 4y divided by x times y minus 3. And we're given some initial conditions here. Y at x is equal to 1 is equal to 1. So we're going to need to use that, but we're not going to use that until later. First of all, we're going to have to try and solve this equation in terms of an unknown coefficient. So let's take a look at that. So taking a look at this equation, you notice that I could rewrite this equation so that it has y's on one side and x's on the other. So this is a separable equation. So if I split that dy dx up into a dy, let's leave that on the left hand side, and multiply by y minus 3 divided by 4y, and this is all equal to dx divided by x. So what I've done there is I've taken all the y terms and brought them over to the other side. And I've taken all the x terms and brought them to the right-hand side. So that's allowed me to write this now as two integrals. So if I put integration symbols on both sides of this equation, you see the left-hand side now is just an equation involving y, an integral involving y, and the right-hand side is an integral involving x. So the left-hand integral we can actually simplify a little bit. We can take that factor of 1/4 out the front. I'm left with y divided by y, so that's 1, minus 3 divided by y, so that's 3 over y dy. And this is equal to the integral dx divided by x. Okay, so carrying out those integrals, these are fairly straightforward. We're left with y over 4 minus 3/4 natural log of y is equal to natural log of x plus a constant coefficient c. So I've done the integral on each side, and you notice that I've only included one constant of integration here on the right-hand side. And the reason for that is if I had included a constant of integration on the left-hand side and on the right-hand side, I could just combine them into a single unknown constant. So I really only need one constant of integration when I carry out the integral on both sides. Alright, so now I still have to figure out what that constant is, and to do that I'm going to use my initial information. So using the fact that when x is equal to 1, y is equal to 1. So that's substituting in x is equal to 1, y is equal to 1 everywhere. We got 1/4 minus 3/4 of the natural log of 1 equal to natural log 1 plus c. And of course, log of 1 is 0. So I'm left with c is equal to 1/4. So now I can write out the full solution, y over 4 minus 3/4 natural log of y equals natural log of x plus 1/4. And I can leave it at that point because I can't really simplify this expression anymore. This is my solution for y in terms of x. It's an implicit equation for y as a function of x. So the next part of this problem asks us to use a substitution to solve a differential equation. So I'm given a differential equation, 3y prime is equal to e to the x, y to the minus 2 plus y. I can't really solve that as it's written, but if I use a substitution here, y is equal to z to the third, and substitute it in here, I'm going to get a new equation, and then I can try and solve that. So let's take a look at how that's going to work. This is part B of this question. So we have a differential equation 3y prime equal to e to the x y to the minus 2 plus y. And we're going to use the following substitution. Y equals z to the power of 1/3. So the way we're going to tackle this is by taking the derivative of this expression on both sides with respect to x, and using that then to get an expression for y prime in terms of z, z prime, and x. So I'm going to eliminate y and y prime from this expression. So to do that, I need to take the derivative of both sides of my substitution. So the derivative with respect to x of y, that is y prime, is equal to the derivative with respect to x of z to the power of 1/3. Now we're thinking about z here as a function of x. So I can take the derivative of z to the power of 1/3 by using the chain rule. So I'm going to have to first of all take the derivative of this thing with respect to z. So that's going to give me 1/3 z to the 1/3 minus 1, which is minus 2/3. And I need to multiply that all by the derivative of z with respect to x. So again, we're thinking about z as a function of x. It's not an independent variable. It's a function only of x, and I can use the chain rule to calculate the derivative of y with respect to x. So now I have both y as a function of z, and I have y prime as a function of z and dz dx. So let's substitute those into my original ordinary differential equation. So I've got 3 times y prime, so y prime was 1/3 z to the minus 2/3 dz dx equal to e to the x y squared y to the minus 2. So again, I'm substituting in here y equals z to the 1/3 plus y. So that was z to the 1/3. So let's tidy this up a little bit, see if it makes some sense. I've got 3 divided by 3, which is 1, z to the minus 2/3 dz dx equal to e to the x times z to the 1/3 all to the power of minus 2. So that's z to the minus 2/3 plus z to the 1/3. So you can see here that I've got this factor of z to the minus 2/3, z to the minus 2/3. So let's multiply everything by z to the 2/3 to get rid of that factor on the left-hand side, to get rid of that factor on the first term on the right-hand side, and get me z to the 1/3 times z to the 2/3, which of course is just z. So I've gotten now the ordinary differential equation I've been asked to derive. And it's an ordinary differential equation in terms of z and x. Now, the fact that I've managed to rewrite that ordinary differential equation in this form means that I can exploit the fact that this is very simple to solve my original differential equation. So I'm going to solve this equation for z, and then I'm going to go back and solve for y. So how do I solve this equation for z? Well, I have a couple of different possibilities. You see that this is a first order differential equation, and it's linear, so I can use the integrating factor method to solve this. So this is a first order linear ODE. So if I rewrite this, I can write it as z prime minus z equal to e to the x. And if I compare that with my first order linear ODE, my standard one, I have dz dx plus p of x times z is equal to q of x. So you can see that p of x is going to be minus 1, and q of x is going to be e to the x. I've just compared my differential equation with the standard form for first order linear ordinary differential equations. I've identified the functions p of x and q of x, and now I'm ready to use the integrating factor method. Okay, so the first thing I'm going to do is I'm going to integrate p of x. So let's just remind ourselves what we're doing. We're calculating the integration factor. R of x is equal to e to the integral of p of x dx. And we're going to use that to solve our differential equation. So the integral of p of x dx is going to be the integral of minus 1 to the times dx, which is just minus x. So my integral of p of x is just minus x. And notice here that I'm not including a constant of integration. As we saw in the lectures, we don't need to include a constant of integration in these integrating factor calculations because they just cancel out in our final solution. So I've calculated the integral of p of x. Now let's calculate r of x. So r of x is the exponential of that, e to the integral of p of x dx. So it's equal to e to the minus x. And that's my integrating factor. I can now use that to calculate the solution. So the solution, we know from the formula, is z is equal to 1 over the integrating factor, integral of q times the integrating factor. And again, the fact that we have an r in the denominator here and an r in the numerator here means that any constants of integration that would have been inserted here would cancel out. So we don't need to include constants of integration when we're calculating r of x. We will need to include those constants of integration in the calculation of the solution, however, as you'll see. So let's put in everything that we've gotten here. We've got first of all, let's calculate that integral of q of x, r of x, dx. So that's q of x was given by e to the x. We saw that r of x was e to the minus x dx. So those exponentials cancel each other out. I've got the integral of 1 dx, which is just x. But I also have to include a constant of integration here. So let's call that constant of integration a. And remind ourselves that we do need to include the constant of integration at this step. Okay, so now that I've got my integral of q times r, I can form the solution. Z of x is equal to 1 over r of x, so that was 1 over e to the minus x, times the integral, which was x plus a. So 1 over e to the minus x is the same thing as e to the x plus a. And notice that that constant of integration here appears in the solution, but it's not just tacked on, it's not just added to the end. I needed to include it at this step here because this is when I did my integral. So I didn't have e to the x times x all plus a, that wouldn't make any sense. So I'm not done yet, however. I still have to find y of x, so I need to go back and use my substitution. Y is equal to z to the power of 1/3. I've just calculated my solution for z, so it's going to be e to the x times x plus a all to the 1/3. Or tidying that up a little bit, I get e to the x divided by 3, x plus a to the 1/3. So there is an example of a problem where I needed to use a substitution to rewrite my equation as something I could solve, and then I needed to use the integrating factor method to solve that. The very last step of the problem was going back and substituting in my original substitution to find my solution in terms of y as a function of x. So the next question that we're going to look at is a second order differential equation. So let's take a look at one of those. So we're going to take a look at question 4 here. So in this question, we've got a differential equation. It's second order. You see here 1/2 u double prime plus c u prime plus 1/2 u is equal to 0. So it's a homogeneous second order differential equation. No right-hand side. And we're looking for the value of c, this damping constant, that will give me the different kinds of solution that I can get for this ordinary differential equation. So overdamping, critical damping, underdamping, no damping, and what we're going to call negative damping. And then we're going to sketch the solution for the case of overdamping and underdamping. Okay, so we're looking here at question 4. Part 1. And let's put down the relevant information. We've got 1/2 u double prime plus c u prime plus 1/2 u equal to 0. So we're thinking here of u as a function of time, let's say. The dependent variable isn't actually specified here, so I'm going to treat t as being my dependent variable. So we're looking for the values of c that gives us the various types of solutions that we can get for this ordinary differential equation. So we're going to have to, first of all, find the characteristic equation for this ODE. So we're going to assume a solution of the form e to the lambda times t. U of t is equal to e to the lambda times t. What that means is that every derivative we take of u turns into a power of lambda. So my differential equation becomes a quadratic equation, an algebraic equation. We're going to solve that for lambda. We're going to look at the different possible solutions we can get for lambda. So let's multiply up by 2 to get this quadratic equation in slightly neater form. And then let's look at the different possible solutions of this. So using the quadratic formula, we have lambda is equal to minus c plus or minus the square root of c squared minus 1. Okay. So that's using the quadratic formula for the solution of this quadratic equation. All right, so now we want to think about the different kinds of solutions we can get for lambda. You can see they're going to be determined by what's going on inside this square root sign. If we have a minus sign in this square root, we're going to get complex solutions here. And we saw that when we have complex roots of my quadratic equation, my characteristic equation, then the corresponding solutions to the ordinary differential equation are going to be sines and cosines. They're going to be oscillations. When what's going on in the square root here is positive, then I'm going to get real solutions and I'm going to get exponential decay. So let's take a look at that discriminant with the term inside the square root and use that to distinguish the different possibilities. So we have when c squared minus 1 is positive, we get lambda 1 and lambda 2 are unequal real roots. And we saw that this was the case we called overdamping. So overdamping will happen when c squared minus 1 is greater than 0. So that's going to occur when c squared is greater than 1 or c is greater than 1. So we know that c has to be a positive number for there to be damping. We saw that in the lectures that c had to be a positive number here in order to have decaying solutions, for there to be damping. If c is a negative number, then this would be actually an increasing solution. So let's take a look at the next possibility, that the square root term actually goes to 0. So if c squared was equal to 1, this term would go to 0, in which case lambda 1 and lambda 2 would both be equal to minus c. So c squared minus 1 equal to 0, which implies that lambda 1 is equal to lambda 2, and those are both real numbers. And that was the case of critical damping. So that's going to occur when c squared minus 1 is equal to 0, or when c is equal to 1. And notice again, I'm not including the possible solution c is equal to minus 1, because that wouldn't give me damping at all. Next possibility is when c squared minus 1 is less than 0. The thing inside the square root is negative, which means I get complex solutions. So lambda 1 and lambda 2 are complex conjugates. And in that case, I get underdamping. I get oscillating, decaying solutions. So that's going to happen when c squared is less than 1, or when c is less than 1. So we have c is less than 1, but we also want it to be positive because we're looking for damping. We want decaying solutions. Even though they're oscillating, we want them to decay. Now we're also asked about the possibility of no damping. That is, when c is equal to 0. In that case, we get no damping. We're just turning off the friction altogether. In which case, we get lambda 1 and lambda 2 are pure imaginary. They don't have a real component. They're just purely imaginary solutions. In fact, they're plus or minus I. In that case, we get sines and cosines with no decay. So that's the no damping case. The last possibility is when we have negative damping. So that's going to occur when c is a negative number. So if c was a negative number, you can see here that my lambda would be equal to something positive, right? In which case, my solution e to the lambda t would be something positive times t. So this would actually be an exponentially growing solution. So clearly that's unstable. That's growing without bound. It's growing and growing, and it's going to what we call the case of negative damping. So of course, real damping is never negative. It will always remove energy from the system. It will cause the system to decay away. So let's quickly sketch what the cases of overdamping and underdamping look like. So we're looking at the case of overdamping, and we're looking at the case of underdamping. In the case of overdamping, we've got two real roots, which means we've got two real decaying solutions with no oscillations. So let's sketch that. So we're going to put t along the horizontal axis. This is time. I'm going to plot what u of t might look like. It has some initial value, and then that decays slowly over time. That's the case of overdamping. We saw in the lectures that in this case, the damping is actually more slow than you might like it to be, because we haven't correctly chosen the friction parameter or the damping parameter that would give us critical damping. What about the case of underdamping? Well, in that case, we're actually getting some oscillations. Better have that actually. So we can have positive and negative values, again plotting t as the horizontal and what u of t might look like. Of course, I don't know the exact initial conditions, so I don't know exactly what this thing is going to look like, but roughly speaking, it's going to have an oscillating nature, oscillating back and forth, but the amplitude of those oscillations decreases exponentially with time. So let's put in the amplitude as a sort of envelope, a dashed line, exponentially decaying. I think I can do a better job of an exponential. Exponentially decaying. There we go, that's better. Likewise, we're going to have the negative amplitudes are also exponentially decaying. So bouncing in back and forth between those extreme values, we have some oscillation that's slowly decaying with time. So that's the case of underdamping. Okay, so we've looked at part 1 of this question. Let's go back now and look at part 2. We're actually given a differential equation with a right-hand side, and we want to show that the solution a cosine t plus b sine t fails to give a solution, and then we want to try and solve this equation with some initial conditions. Let's take a look at that. So this is part 2 of question 4. So we're told that u double prime plus u equals to cosine of t, and our first step is to show that u equals to a cosine t plus b sine t is not a solution of this equation. So all we're going to do is we're going to just take derivatives of that and substitute them into our differential equation and show that it doesn't work. So I've got u prime is equal to minus a sine plus b cosine, and I've got u double prime is equal to minus a cosine plus minus b sine. Substitute those into my differential equation. On the left-hand side, I get u double prime, which is minus a cosine t minus b sine t, plus u, so that's plus a cosine t plus b sine t, and you see that we get exact cancellation between those two terms. So this term cancels with that term, and this term cancels with this term. So we get the left-hand side is equal to 0, which means that the left-hand side is not equal to the right-hand side, implying that this is not a solution. If this was a solution, of course, if I substitute it in to my differential equation, I should find that both sides are the same. So this is not a solution. Okay, so we're going to have to look for the correct solution. And we're going to do that by, as usual, breaking it up into two parts. We're going to break it up into its homogeneous solution. So u is equal to u homogeneous plus u particular solution. So the homogeneous solution solves this equation. Just set the right-hand side equal to 0. We're going to look for solutions u h equal to e to the lambda t, which turns every derivative into a power of lambda and gives me the following characteristic equation: lambda squared plus 1 is equal to 0. This has solutions lambda is equal to plus or minus I, which means that my homogeneous solution is a times cosine t plus b sine t. But we know from part A that that's not the full solution. If I substitute this in to my differential equation, I don't get a solution. It doesn't balance out the right-hand side. So I still need to find the particular solution to deal with that right-hand side. So choose for particular solution, or trial solution. What are we going to choose for that? Well, we're going to first of all look at the right-hand side of our differential equation. So our differential equation, again, let's pull that up, is u double prime plus u is equal to cosine of t. So the right-hand side is a trig function. You'd think I would just choose the most general possible trig function as my particular solution. But we saw that my homogeneous solution is already the trig functions, cosine t and sine t. So what I'm going to have to do is to form a new solution by multiplying by t. So it's going to be, instead of cosine t, it's going to be t cosine t. And instead of sine t, it's going to be t sine t. And I've put in some undetermined coefficients d and e there that I'm going to determine now. So again, we couldn't just put in cosine and sine there, because those are already solutions of the homogeneous equation, the equation with 0 on the right-hand side. To solve for the particular solution, I need to invent a new solution, which I do by multiplying those by t. Now I'm ready to substitute this trial solution into my differential equation to figure out what d and e are. So let's do that. We're going to calculate the derivatives of this. So the derivative, first derivative is going to be d cosine t. I have to use the product rule a couple of times here. Minus d times t times sine t plus e sine t plus e times t times cosine t. We also need the second derivative. So that's going to give me minus d sine t minus d sine t minus dt cosine of t plus e cosine of t plus e cosine of t minus e times t times sine of t. So tidying this up a little bit, we get minus 2d times sine of t minus dt cosine of t plus 2e cosine t minus e t sine t. Right, so we're ready now to substitute this into our differential equation. So let's substitute this into u double prime, u subscript p double prime plus up is equal to cosine t. So up double prime, we just calculated that. It's minus 2d sine t minus dt cosine t plus 2e cosine t plus, minus et sine t. And we're going to add to that up, so that was dt cosine t plus et sine t. And this whole thing is equal to cosine of t. And you notice that we get a bunch of cancellation here. The dt cosine t's cancel out and the et sine t's cancel out. And that'll always happen so that we're only left with terms like sine t and cosine t. So we can match the terms appearing on the right-hand side here with the corresponding terms appearing on the left-hand side. So you can see that there is no sine t term on the right-hand side, which implies that d must be equal to 0. On the other hand, matching the cosine t terms, we get 2e cosine of t is equal to cosine of t, which gives that e is equal to 1/2. So my particular solution, up, is going to be given by dt cosine, so that was 0, plus e t sine t. And to form the full solution, I have to put back in what the homogeneous solution was. So it's the sum of the two, homogeneous subscript h plus particular subscript p is going to be a cosine t plus b sine t plus 1/2 t sine t. So you notice that our final solution here, our full solution, only involves two unknown constants of integration. This is a second order differential equation, so the most number of unknowns that can still be in here is 2. And the other unknowns, d and e, are fixed by the method of undetermined coefficients. Okay, so we're going to move now to question 5, which is a question involving resonance. Let's take a look at that. So in question 5, we're asked for the general solution of this vibrating system. And we're asked, will the system exhibit resonance for any choice of the forcing frequency? So let's take a look at that. We've got, again, a second order ordinary differential equation. It's non-homogeneous because it's got a right-hand side. So we're going to have to use the method of undetermined coefficients again. Okay. So question 5, part 1. We're looking for the solution of d squared y dt squared plus 2 dy dt plus 2y is equal to sine omega t. So to find the solution, we're going to write y is equal to the homogeneous piece plus the particular piece, where the homogeneous piece solves the equation with no right-hand side. So I'm going to use primes to denote derivatives with respect to t. That's my homogeneous equation. Let's assume a solution of the form YH is equal to e to the lambda t. Every derivative turns into a power of lambda. Gives me a quadratic equation for lambda that I can solve. So lambda is going to be equal to minus 2 plus or minus the square root of 2 squared minus 4 times 2 times 1, all divided by 2. So that will be minus 1 plus or minus a half times the square root of 4 minus 8, so that's the square root of minus 4. So we get lambda is equal to minus 1 plus or minus I. Square root of minus 4 is 2i, and then I'm dividing by 2. So I've got complex solutions here, which means that my homogeneous solution is going to be e to the real part times t times a cosine imaginary part, so that's a 1 times t, plus b imaginary part, sine of imaginary part times t. So my solution is an exponentially decaying oscillation back and forth between plus and minus 1. Okay, so I have my homogeneous solution. Now I need to find the particular solution that will deal with that right-hand side. So let's go back and take a look at my right-hand side. It's sine omega t. And you can see that there is no danger that my homogeneous solution is going to match my right-hand side, because I've got this e to the minus t here. So there's no danger of sine omega t looking like e to the t times cosine, or e to the minus t times sine. So I'm free to choose my particular solution to be of the form. The most general possible trig function, so let's call it c cosine, with the same frequency, omega t plus d sine omega t. So the derivatives of that then are going to be minus c times omega sine plus d times omega cosine. Second derivative will be minus c omega squared cosine minus d omega squared sine. Let's substitute that now into my ordinary differential equation, non-homogeneous, so that was yp double prime plus 2yp prime plus 2yp is equal to sine omega t. So I'm going to get yp double prime, that was minus c omega squared cosine minus d omega squared sine plus 2yp prime, so that's going to give me minus 2c omega sine omega t plus 2d omega cosine omega t. So that factor of 2 there is coming from here, this factor of 2, yp prime. So I'm just substituting this line in instead of yp prime, and I'm going to now put in 2 times the first line. So plus 2c cosine omega t plus 2d sine omega t. And that, of course, all has to be equal to the right-hand side, which was sine omega t. So let's gather together the like terms, the cosines and the sines. So I've got cosines, I'll underline in green, cosine, cosine, cosine. Sines I'll underline in pink, sine, sine, sine. So I'm going to get, let's see, I've got a 2c minus c omega squared plus 2d omega, all times cosine. And I've got a 2d, I've got a minus d omega squared, and I've got a minus 2c omega, so that's going to be plus 2d minus 2c omega minus d omega squared times sine omega t. And that's all equal to sine omega t. So if I match the coefficients of the cosines and the sines on each side, I get two equations for two unknowns. So I get, there's no cosine term, so the first term in brackets is 0. And there is a sine term, so that term will just be equal to 1, the term in brackets. So here are two equations for two unknowns, c and d. I will leave you to solve for those expressions. They're given in the full solutions, which are posted on the Moodle forum. But you'll find that the full solution, y of t, is equal to, remember we have to include our particular piece, so that was e to the minus t a cosine plus b sine. And the particular piece is going to be given by this expression here. So you're going to have to do a little bit of solving of simultaneous equations. Not too hard, just a little bit time consuming. You'll find solutions that look like this. So the last part of this question asks us, is there any value of omega that will give us resonance? Now remember that resonance occurs when my forcing matches my natural frequency, the natural way that this system wants to respond. And remember that the natural way the system wanted to respond was in this form here. It was given by the homogeneous solution to the equation. If there's no forcing, the system is just going to do what it's going to do. And we saw that this is going to oscillate at e to the minus t, a cosine t times plus b sine t, right? So there's going to be a exponentially decaying oscillation, and the oscillation is going to occur with a frequency of 1. On the other hand, we're asked, we can ask what happens when I force this system with a frequency of omega. So I get a response cosine omega t and sine omega t. So you see there's no value of omega that I can choose that will match this expression here because of the role of this e to the minus t. So this system does not exhibit resonance for any value of omega.